Morning, students. In our last lesson of analog electronic circuits, we have discussed what is the design approach of a small signal BJT common emitter amplifier. Yes, mathematical relations and various empirical considerations that have to be taken care of, everything has been discussed. Also, we have discussed the purpose of various components. Today, are going to actually design an amplifier, small signal amplifier. This is your amplifier. This is your amplifier. Today we shall actually design. Step 1. Consider 8547. As I said, it's a very common low power BJT. No problem. You can always find it in your laboratory. Then you should first measure the beta with a multimeter. Nowadays, all digital multimeters have give a facility of beta measurement. Measure the beta with the multimeter. But now I cannot show you how I measure with the multimeter. What I do, I take beta 300 and VB equal to 0.7 volt because that is given by the software that I am going to use in front of you for designing this amplifier. So I take beta 300, VB 0.7 volt, right? Also, we take a power supply. What is the power supply? 10 volt. 10 volt is a reasonably good power supply. Here, my advice, don't take very high voltage. You can even take 100 volt, doesn't matter. You have to only see the transistor manual, whether BJT 547 will be able to tolerate 100 volt. But don't work in your laboratory with a very high voltage. I would say do not work in your laboratory with a voltage of more than 15 volt because that is in order for your personal safety against electrical shock. So as a good value is a 10 volt. Then, as we discussed earlier, we consider RL, load resistance is 10K. Actual load resistance will be always more than 10K. So if I take 10K, my design is always safe. In practice, if it comes out to be more than 10K, then amplifier will perform better. Next, here I request you, all of you, please take note of the steps, which one after what, right? So first BJT, then note its beta and VBE, then consider the voltage, supply voltage 10 volt, consider RL 10K, then consider RC. As I said earlier, in my last lesson, RC you take not more than RL by 10. RL by 10 is 1K, so don't take more than 1K. 1K is a good value. Don't take too low also because then there will be a very high DC current through the transistor, 1K. So that RL in AC load line, effect of RL in AC load line is minimized. Next step, much lower than this RE, much lower than RC. Empirically, we take RC by 5. Once again, I said, much of AC power is lost in RE. In spite of this capacitor being there, some AC current may flow through this RE because a capacitor, its impedance is 1 by omega C. So it is never zero. It is never zero. You can make it small, but not zero. So always there is a signal loss in RE. So you take the value of RE small, which is empirically RC by 5. RC is 1K, so RE is 200 ohm, right? In your laboratory, you can use 200 ohm resistances in series. That will make 200 ohm. In that case, you remember our last lesson, we talked about RAC, RDC. What is RAC? RAC is RC and RL in parallel. C is 1K, RL is 10K. If you calculate their parallel combination, it is 909 ohm. And what is RDC? Is RC plus RE. It is 1K plus 200 ohms, so 1.2K. Fine. Next step. What is ICQ? I have shown you the formula. It is VCC divided by RAC plus RDC. VCC is 10 volt, RAC is 909, RDC is 1.2. You calculate, it will become 4.74 milliamps. So, my quiescent collector current will be 0.74 milliamps. And quiescent collector voltage will be, once again, by the same calculation, is 4.74 milliamps multiplied by 1K is 4.74 volt. Incidentally, two numeric values are same, but it need not be same always. 4.74 volt, right? So, uh, so what is the power dissipation in this transistor? 4.74 milliampere and 4.74 volt. Say 5 milliampere, 5 volts. So 25 milliwatt. You cross check. BC547 can take for 25 milliwatt. I know it can take up to 100 milliwatt. So my transistor will not be red hot. There will be no problem. Next step. We are still in the design procedure. Consider the input equivalent circuit. This input equivalent circuit is this signal source, then this capacitor, then parallel combination of R1 and R2 make RB and VBB, and this is VBB. This potential divider voltage here is VBB, this is VBB, then this is VBE, that is reverse junction voltage, which works as a hypothetical power source, voltage source, reverse junction voltage, and RE comes here at beta RE. I think you have learned this in your device classes because the drop in RE is IERE. That means emitter current into emitter resistance. Right. Now, emitter current is beta times the base current. So if you look from the base side, it is as if the resistant itself is beta RE. That is the easiest way to understand this. So this is my equivalent input circuit. With this equivalent input circuit, I have earlier found ICQ is 4.74 milliamps. So what is IBQ? IBQ is ICQ by beta. Beta we have no 300. So IBQ is 0.016 milliampere approximately, right? All calculations. Then what is the value of RB? RB also we have earlier learned should be beta RE by 10. So 300 into RE is 200 ohm by 10 is 6 kilo ohm. So RB we got 6 kilo ohm, right? Then what is VBB? Now look at this VBB. Look at this circuit. VBB equal to this ohmic circuit. VBB equal to RB IBQ, RB IBQ, this current, plus this reverse voltage VBE, plus the current flowing through this is beta RE into IBQ. If you calculate all these things, VBB voltage becomes 1.76 volt. That means you want a potential divider here to be designed in such a way that 10 volt is divided here to 1.76 volt. So now you have to decide R2 and R1 so that this is 1.76 volt. Of course, here you have many options. For example, let us consider your VBB is 5 volt, right? Hypothetically, 5 volt. Then VCC is 10 volt. You want 5 volt here. So if you take two equal resistances, then it will become 5 volt. Now, two equal resistances can be a 10 kilo ohm and another 10 kilo, or can be a 1 ohm and another 1 ohm. It will, in both cases, it will be 5 volt here. But how do you decide that? With much of DC current flowing through this line, because then these resistors will get hot. Even it can create a problem of with this power supply if this power supply cannot supply that much of current. So in this line, if it is a 10 volt, in this resistance should be resistance is 10K, then a current flowing through this line is 1 milliampere. I would say you still make it lower. Still make it lower. Both of these together, you make maybe 12 kilo ohm or 15 kilo ohm, something like this. These are practical design considerations, right? So anyway, so here you have a liberty to choose R1 or a liberty to choose any one of them, and the second one will come out of calculation. Say I am going to choose R2. What I do, I choose R2 is equal to 2.2K. 2.2K is a standard value. If I take R2 is equal to 2.2K, then this VBB is equal to VCC divided by 2.2K plus R1 multiplied by 2.2K. If you calculate this, R1 becomes 10.3K, right? So in this line, you have 2.2 and 10.3. Both together become something around your 13K. So current flowing through this line will be less than 1 milliamp, and that is good, right? And 10.3 is not a standard value. You take 10.27. Now 10.27 is also not a standard value. What do you need to do? You have to take a 10K resistor in series with a 270 ohm resistor. This 10K, 270, both are standard resistors. You can get it in your laboratory. So you use 10.27. So these are the practical considerations. Do not consider a value which you will not get in your laboratory. Like say you have taken here 6K. RB, of course, I don't have to get a resistance. R2, I have taken 2.2K, right? So if you make it 2.3K, then you don't get that value there in the laboratory. So you get here 2.2 and 10.27K, right? Then, so we have decided these values. Lastly, let's determine the value of these three capacitors, right? Impedance of a capacitor is 1 by 2 pi fc, rather 1 by omega c in and our signal frequency is 1 kilohertz. Signal frequency, mind it, this baseband frequency, as I said, if you were taking audio frequency, suppose you are using this amplifier to amplify a mic, signal from a mic, then frequency will be something like 500 hertz to 3 kilohertz, like that. But normally, all audio amplifiers we test at 1 kilohertz, right? So we calculate on the basis of 1 kilohertz. And also, after actually designing the amplifier, we are finding that I need to change the capacitance value. You can always change it by picking up another value from in your laboratory. But testing of the signal is always done at 1 kilohertz. Now, at the signal frequency, this CE must be much lower than RE. Here, our empirical rule is make it 1/100th of RE or even smaller. Because this RE, the signal current drop in RE it affects the amplifier gain. So make C very small. I'll test it at 1 kilohertz, but mind it, my audio signal is much less than 1 kilohertz. So make it 1/100th. So 1 by 2 pi f is 1000, C should be less than my RE is 200 ohm by 100. From here you can find out C is 80 microfarad. Take a standard value of higher side 100 microfarad. Next, impedance of CO. We said earlier in our last lessons, impedance of CO must be 1/10 of RL or less. Then applying the same calculation, we found CO is 0.16 microfarad, right? So we go on a higher side because that is always a safer side. We take 1 microfarad, right? Of CI input coupling capacitor should be 1/10 or less of RB in parallel with beta RE, because this signal current is facing a parallel impedance of RB and beta RE, right? Because AC sources are short circuit for the signal frequency. So 1 by 2 pi FCI should be less than 1/10 of RB beta RE in parallel. RB is 6 kilo ohm, beta is 300, RE is 200 ohm or 0.2 kilo ohm. So all these calculations, CO becomes 300 microfarad. We take a standard value of 330 microfarad. So we have decided all the values of this amplifier. The list of this amplifier: BJT 547, VCC 10 volt, load resistance 10K, RC, this resistance is 1K, RE, this resistance is 200 ohm. By the way, uh, in electronic media, the ohm signal is not always available, so often they write E. R1, this top resistance is 10.27K, R2, this bottom resistance is 2.2K, emitter bypass capacitor is 100 microfarad, output coupling capacitor is 1 microfarad, input coupling capacitor is 330 microfarad. And if we do that, expectedly, VCQ will be 4.74 volt and ICQ will be 4.74 milliampere, right? Next day, or in our next lesson, what we shall do, we shall use these values and actually test this amplifier on simulation. Now here I give you a caution. When you test this on simulation, sometimes you may become frustrated. Not because of your fault, any fault of yours. You might have designed it perfectly, but frustration is due to the values that you put in here. All of them have many tolerances. Primary JT that you are using, it has got so many factors and so many tolerances. And considering all those tolerances, you may find your amplifier gain is not what you want. So in that case, what do you do? You have to intelligently, slightly alter these values. And if necessary, during simulation, I'll show you what is that intelligence. Because you always need to know that suppose you have to change R2. You need to know what will happen if you change R2, right? And that we have discussed everything in our earlier lessons. Suppose you have to change CE. You need to know what will happen if you change CE. Accordingly, we do those changes. And this test we shall do in our next lesson. And today's last point is my request once again please subscribe to this channel because that gives me enthusiasm. Because if I do not get any feedback from my students, then I do not know whether all this effort is going to drain or it is at all useful, right? So here we end our lesson today, and next day we shall see the actual amplifier design.